it as the backbone of the DSP world. The reason of the popularity of FFT is that it offers its applications almost everywhere. It enables us to perform spectral analysis of the given data in real time. Suppose we want to plot spectrograms of the given speech signal, then FFT will be used in making spectrograms. And spectrograms are considered as the most important feature in speech recognition systems. So FFT plays a very important role during the feature extraction phase of speech recognition systems. Similarly, if you want to perform power quality assessment of electric power systems, then FFT can also be used there to analyze the harmonic content or harmonic distortion present in power systems. Similarly, when we write audio files in MP3 format, then FFT plays a significant role in MP3 compression as well. Similarly, you will find a lot of applications of FFT in healthcare sector as well to analyze ECG signals, EEG signals, and many more other signals. So FFT offers its applications in a wide variety of fields, including telecommunication sector, electric power systems, healthcare sector, sound applications, data analytics, and many other fields. Now, what is FFT? FFT is just a faster way to calculate discrete Fourier transform. So any algorithm or any technique which will implement the standard DFT equation in an optimized manner will be called fast Fourier transform. Now the question is why FFT is required. As we already discussed in the previous lecture, in a standard DFT, the number of computations depend on the order of n square. So if you will increase the value of n linearly, the requirement of computations will increase non-linearly, which makes DFT implementation very slow due to the repeated number of calculations performed by it. That's why we require some optimized algorithms which will implement the same DFT equation but in a faster way. So fast Fourier transform is just an optimized implementation of the discrete Fourier transform. And what is the need for speed? The basic objective of implementing FFT is that we want to perform harmonic analysis in real time even if the value of n is very high. Okay, the FFT algorithm which we will discuss in this course is radix 2 FFT algorithm. There are several other radix based FFT algorithms like radix 4, radix 8, radix 16, radix 32. Now, why we have selected radix 2 FFT algorithm? Because it's the most fundamental one. After gaining understanding of radix 2 FFT algorithm, you can get an idea about how other radix based algorithms will work. So you can develop radix 4, radix 8, 16 or any other radix based algorithm, but you must have a very clear understanding of the radix 2 FFT algorithm. That's why we have selected this algorithm. So in this lecture, we will see how radix 2 FFT algorithm can be implemented on a given time domain sequence. Now let's come to the condition of radix 2 FFT, which is the mandatory condition. The condition is that the length of signal or the number of samples must be expressed in a power of 2. Or mathematically we can say that n should be equal to 2 raised to power k, where k could be any positive integer. Which means that if the length of signal is 2 samples, 4 samples, 8, 16, 32 or any power of 2 samples, then in only that case we can apply radix 2 FFT algorithm, otherwise not. So this is the condition which we must have to follow if we want to perform harmonic analysis through radix 2 FFT. Now let's come to the case where signal length is not perfectly equal to 2 raised to power k samples. Let's say n is equal to 13 samples, which cannot be expressed in any power of 2. So radix 2 FFT cannot be applied directly on the 13 samples. We must have to convert this number into some 2 raised to power k. So as we already know, 13 is in between 8 and 16, which can be expressed in a power of 2. So in such cases, we have two options. Option 1 is about samples truncation. In this method, we can select any 8 consecutive samples of the original signal. so that we can apply 8-point radix to FFT on it. But in this case, we must have to discard the remaining 5 samples. And this option is usually avoided because of some disadvantages. Definitely when we will discard some samples from the original signal, then it will cause a loss of information. Similarly, when we will decrease the value of n, then the resultant DFT frequency resolution will also get worsened. So this option is usually not preferred during spectral analysis. Now let's come to the second option. Second option is about zero padding. In order to make the signal length equal to 16 samples, we have to introduce 3 samples in the original sequence. So what samples we can introduce in the original sequence? We can introduce or append 3 zeros in the original sequence in order to make it 16 samples. And those 3 zeros can be introduced either at the start or end of the sequence, so that we will get a sequence equal to 16 samples. And we can apply 16-point radix to FFT on it. So the idea is we can introduce any number of required zeros in order to get the desired value of 2 raised to power k samples, and this is the option which is used practically. Now let's discuss what exactly the approach of radix to FFT algorithm is. The idea of radix to algorithm is, instead of taking an n-point DFT on a given n-point sequence, first split the original n-point sequence into smaller point sequences of equal lengths and then take their smaller point DFTs. And after calculating smaller point DFT outputs, merge all the smaller point DFT outputs in order to construct the overall n-point DFT output. So this process of first decimating or decomposing and then reconstructing the smaller point DFT outputs will cause a significant reduction in the number of computations as compared to the standard DFT implementation. Now let's assume the signal length is equal to 16 samples. So in accordance with the radix to FFT algorithm, we will not take 16-point DFT directly on the given sequence. Before calculating DFT, we will split the original sequence into 2 sequences of equal lengths where each sequence contains 8 samples. Now radix to FFT algorithm says you can calculate 8-point DFT of both sequences and then merge their outputs in order to get the overall 16-point DFT output. Now the question is, what benefit we could have by splitting original sequence into smaller sequences? The answer is computational reduction, because the number of computations are a function of n square in the case of DFT. So if we will perform the same task by using a smaller value of n, then definitely it will need lesser computations. For example, let's take an example of complex multiplications which are equal to n square. So if we will split the original sequence into these two sequences, then the first 8-point DFT will need 64 complex multiplication. The second 8-point DFT will also need 64 complex multiplication, which makes it 128 complex multiplications. While if we will take 16-point DFT, then it will take 16 square, which means 256 complex multiplications. So this is the reason for splitting original sequence into smaller sequences and then take their smaller point DFTs. Now the question is, can we split these two sequences where each sequence contains 88 samples into further smaller sequences? So the answer is yes. We can split both sequences into two sequences where each sequence will contain 4 samples. So we can calculate the 16-point DFT with the help of 4-point DFTs. Now, can we split these 4 sequences into further smaller sequences? So the answer is yes, we can split all these 4 sequences into smaller sequences where each sequence will contain 2 samples. So in this case, we have represented an original sequence of 16 samples into 8 sequences where each sequence is containing 2 samples. Now, Can we split these 8 sequences into further smaller subsequences of equal length? So the answer is again yes. We can split each sequence of 2 samples into 2 sequences of equal length, where each sequence will contain only one sample or a single sample. So this is the last stage which we could have if the value of n is equal to 16, because we cannot proceed further, we cannot further decimate it, we cannot divide a single sample into any other sample. So in this case, we have represented an original sequence of 16 samples into 16 sequences, where each sequence contains only one sample. Now let's observe a relation between n and the number of stages. As you can see, the value of n was 16 and we have decimated the original sequence into 4 stages in order to get a sequence which contains only single sample, which is the last stage of this process. So n and number of stages are related through log base 2 of n, because if n is 16, then the total number of decimation stages will be log base 2 of 16, which will be equal to 4. Similarly, if the value of n is equal to 1024, then the total number of decimation stages will be 10, because log base 2 of 1024 is simply 10. So it's a very important relation between the value of n and the number of decimation stages, which we could have before calculating Fourier transform. And the process of representing an original sequence of n points into smaller sequences is called decomposition or decimation in time. Here you can see the total number of complex multiplications in each of the 5 possible cases. If we take 16-point DFT directly, then it will need 256 complex multiplication. Suppose we are implementing 16-point DFT with the help of two 8-point DFTs, then in that case 128 complex multiplications will be required. And if we are representing our 16-point sequence into 4 sequences, where each sequence contains 4 samples, and we perform all our calculations with the help of 4-point DFTs, then in that case we will need 64 complex multiplication. Same is the case for the subsequent stages. If we will represent 16-point sequence into 8 sequences of 2 samples, then in that case DFT will need 32 complex multiplication. And if we have represented an original sequence of 16 samples into 16 sequences, where each sequence contains only one sample, then in that case DFT will need 16 complex multiplication. So this is the main benefit for performing full decimation in time. Full decimation in time means we are calculating Fourier transform at the most fundamental level, where we have represented every sequence by a single sample. Now, after performing decimation or after rearranging the sample values of an original sequence, now we will reconstruct the overall output. So this map is so called the reconstruction map, which is totally opposite to the decimation map. After representing an original sequence of 16 samples into 16 sequences, where each sequence was containing one sample, we will take 1-point Fourier transform of all those sequences, and 1-point DFT will return 1 point as an output, which are shown here. Now these are the 1-point DFT outputs, and our task is to reconstruct the overall 16-point DFT output, because our objective was the calculation of 16-point Fourier transform calculation, not the 1-point Fourier transform computation. So with the help of these 16 single point DFT outputs, we will try to reconstruct the overall 16-point DFT output. But this reconstruction cannot happen directly. With the help of single point DFT outputs, we will reconstruct 2-point DFT outputs in the first stage. Then after the first stage of reconstruction, we will find 2-point DFT outputs. With the help of these 2-point DFT outputs, we will reconstruct then 4-point DFT outputs. And with the help of these 4-point DFT outputs, we will reconstruct the 8-point DFT outputs. And with the help of these two 8-point DFT outputs, we will reconstruct the final 16-point DFT output. So in this particular way, we can calculate the 16-point Fourier transform. This is the basic idea of radix to FFT